Here we see all the characteristics of alpha, beta, and gamma radiation. Again, alpha radiation emits an alpha particle, which is a helium nucleus, has a charge of 2 for the 2 protons, atomic mass unit of 4 because there's 2 protons and 2 neutrons. For the beta radiation, a neutron is decomposing into a proton and an electron. And so you're emitting this electron out of the nucleus, that's the beta particle, and so you have the same mass as an electron, same -1 charge as an electron. And gamma radiation is just high energy light. It is photons of electromagnetic radiation. It is more energetic than X-rays. It is super energetic. Light travels at the speed of light. Beta particles travel almost the speed of light at 90%. Alpha particles travel at 10%. And again, a beta particle is an electron. Alpha radiation emits helium nucleuses, and gamma radiation releases high energy photons of light. If we look through the uranium disintegration series, we'll notice that uranium first loses an alpha particle, and then it goes through 2 beta decays, and then those 2 neutrons become protons. And so we look at the atomic number. It was at 92. It goes down to 90 because we lost an alpha particle, which is 2 protons and 2 neutrons. But now the proton number goes back up 2 because in those 2 beta decays, neutrons became protons. Now we lose another alpha particle, another one, and another one to get to polonium, and one more to get to lead-214. And this is a radioactive form of lead. It's not stable lead. This will end up as lead, but not lead-214. And I know it's 214 because over here on the left side of the graph are the mass numbers. So here we now have 2 more beta decays, and we get back to polonium. We're at polonium-214. Now we release an alpha particle, and we end up with lead-210. 2 more beta decays, and we get to polonium-210, and then one last alpha decay. And now we get to a stable isotope finally, lead-206. And this is one of the reasons that you find so much lead on Earth, is because all radioactive isotopes typically end up as lead-206. It's your very first stable isotope, stable nucleus that exists in the periodic table as you're decaying down from these super heavy elements. So if we follow this path, we lose 1, 2, 3, 4, 5, 6, 7, 8. You lose 8 alpha particles, and there were 6 beta decays. And so in the end, 1 atom of uranium ends up being 1 atom of lead-206, and also there are 8 atoms of helium. So 1 atom of uranium will end up becoming 1 atom of lead and 8 atoms of helium. And that is why you look for helium in the ground. It is a byproduct of alpha radiation, and it builds up in areas that had a lot of uranium-238. So which nuclide is formed when 238 undergoes alpha decay, followed by 2 beta decays? Well, if you do an alpha decay, we lose 4 in the atomic mass and 2 in the atomic number, getting to thorium-234. But now there's 2 beta decays, which means 2 neutrons become protons, pushing us back to uranium-234. So we started with uranium-238, and now we're at uranium-234. Transmutation. This is the conversion of one element into another by natural or artificial means. This all started with the alchemists when they were trying to turn lead into gold, because lead was cheap and gold was expensive, so they thought it was financially brilliant. Unfortunately, thousands of years ago, they did not have the technology to accomplish this. However, these days we can. We do purposely produce elements. Technetium is not found on Earth. It is produced in a bombarder for medical isotopes. So transmutation can occur naturally through radioactive decay, or it can be man-made. For example, certain reactors produce plutonium. So there are definitely elements on Earth that are made on purpose by people that would not exist normally. The first artificial transmutation was occurred in Rutherford's lab, in which nitrogen and helium reacted to form oxygen-17. So anytime you start with one element and end up with a different element, that's transmutation. Several elements have been made by transmutation in particle accelerators. And in a particle accelerator, electrons and positrons are accelerated in long tunnels, and particles are sent through long tunnels and build up massive amounts of energy. So when they collide with each other, it's an extremely energetic reaction. Examples of forming californium. We have uranium-238 is smashed into a carbon-12, and we get a californium-244 and 6 neutrons emitted from this reaction. Roentgenium, bismuth-209 is smashed into nickel-64, and we get Rg-272 and a neutron. Irene and Frederick Joliot-Curie discovered that bombarding aluminum-27 with alpha particles, neutrons and positrons were emitted. Initially, phosphorus-30 was produced along with a neutron. Silicon-30 was then produced with a positron. And again, a positron has the same mass as an electron but opposite charge. It is the antimatter particle of an electron. Artificial radioactivity is produced by bombarding stable isotopes with small particles, typically neutrons or alpha particles. And they received the Nobel Prize in Chemistry in 1935 for this discovery of artificial radioactivity. Geiger counters are used to measure radioactivity. And ionizing radiation is high enough energy radiation that it causes atoms or molecules to ionize. It rips electrons off of them and they get a charge. And if the ionizing radiation enters the Geiger counter, argon, the noble gas argon, is ionized and an electric current passes between the electrodes. Radiation is measured in counts per minute of this ionization process. So basically, it forms a plasma. You have a gas, the gas gets ionized, now you have a plasma which is capable of conducting electricity, which allows the electric current to pass, and you get a tick on the Geiger counter. A curie is a unit expressing the amount of radioactivity produced by an element. 1 curie is 3.7 times 10 to the 10th disintegrations per second. And this is defined from the radioactivity of radium, which has a radioactivity of 1 curie per gram. A curie is a large unit, so really milli or microcuries are commonly used in actual experimental chemistry. And other radioactive units. We have Roentgens, we have rads, rems, and grays. The gray is the SI unit. It's the amount of radiation energy absorbed by tissue, joules per kilogram of tissue. A rem accounts for the degree of biological effect caused by the type of radiation exposure. For example, alpha radiation is 10 times more ionizing than beta radiation. And so that factor of 10 is also used because it's 10 times more damaging to living tissue. Nuclear fission is when a heavy nuclide is bombarded by a neutron and splits into 2 or more intermediate-sized nuclides. And here we see uranium-235. When a slow neutron strikes it, breaks apart. And this is how the atomic bomb was first made. The rush in the 1930s to produce an atomic bomb led to a lot of research in radiation and nuclear fission in how to split uranium and harness that energy from that. And these days, nuclear power plants do the same thing, except in a very controlled fashion to make enough energy to produce electricity. Alright, so in nuclear fission, large amounts of energy are produced. And you also end up with a lot of radioactive spent fuel. So in the fission process, a neutron, and it's called a slow neutron. The speed is actually really important. It has to be the exact correct speed when it hits the nucleus to make it split. And this uranium, because we had a neutron and it hit uranium-235, you temporarily get uranium-236 because you have that extra neutron, but then that's not stable to exist, and so it splits into 2 products. And our fission products are 3 neutrons, which will go off to split other uraniums. So these guys can all split other uraniums. And you'll have two nucleuses coming from this. Mass numbers anywhere from 85 to 105 for one, and from 130 to 150 for the other. So it's not the exact identical products each time, but they're within this range. So you get 2 nuclides and 3 neutrons, which means each one of these fissions can produce 3 neutrons, which can cause 3 more fissions, and each of those can produce 3 more fissions. And so this is a chain reaction that can go out of control really quickly, which is why atomic bombs blow up the way they do. If you let the reaction occur completely uncontrolled, it just blows up. In a nuclear power plant, you have control rods full of cadmium that you can lower to absorb the neutrons. And so those act kind of like a brake, where you can lift them or lower them to slow or speed the reaction as you see fit. Chain reaction, a radioactive decay where the products cause the reaction to continue or magnify. As we just said in that last fission reaction, we get 3 neutrons flying out, which can keep the reaction going. The critical mass is the minimum amount of an element needed to support a self-sustaining chain reaction. Because energy is released during each fission event, chain reactions provide a steady supply of energy. So energy is released every time there's a fission event, and uranium is broken up into 2 pieces. And you have 3 neutrons that can cause more of that to happen, but you're producing energy to keep the reaction going. So a chain reaction can easily get out of hand. And that's what we're seeing here. A nucleus of uranium-235 absorbs a neutron, undergoes fission, and produces 2 fission fragments and 2 neutrons. One fission fragment is xenon-144. What is the other? And that's going to be strontium-90. Because the uranium absorbed a neutron, and then when that breaks apart, we get xenon-144, strontium-90, and 2 free neutrons flying away from this. So again, a nucleus of 235 absorbs a neutron, which is what we're seeing right here, and produces 2 fission fragments and 2 neutrons. And that's how we knew that 2 neutrons were flying out right there. And so 2 neutrons make up 2 atomic mass units. We started with 236 atomic mass units. Remember, mass has to be the same. And if xenon is 144, we need 90, strontium 90. And so in the end, 144 plus 90 gets us to 234, plus 2 gets us to 236. Total atomic mass unit of 236. And on this side, 235 plus 1 is 236. So again, it's important to remember the conservation of mass. You start with 236 atomic mass units. You must end with 236 atomic mass units. Nuclear power plant is a thermal power plant where heat is produced by a nuclear reactor. So we have a nuclear fuel. Basically, it's uranium, but it has to be 10% enriched, which means 10% of the uranium has to be uranium-235. Anything less than that, and it's not going to work. The uranium-238 is not active enough. So you need 10% enrichment for a nuclear power plant. To make a nuclear bomb, you need over 90% enrichment. And then this heat is used to boil water. The steam spins turbines. You produce electricity. And then there's got to be a cooling system to condense that steam. So pretty much these tubes are run through rivers. And so this causes thermal pollution. Typically, a river is 4 degrees warmer after the nuclear power plant than before it. So here we see our schematic. Here's our reactor core. It gets super hot. This energy is used to boil water into steam. Steam pushes a steam turbine, produces electricity for a city, comes back to a condenser, and now the river water is actually used to cool it. The river water does not touch the radioactivity. You have really thick lead pipes here, so that doesn't happen. But what you're using is the energy, and so the river water is absorbing the energy of the steam to condense it back to water so it can go through this cycle again. And the river is now a lot warmer. So again, here you see cool water coming in. Here's the cool water coming in. It absorbs all this energy, and now you have warm water. So you have thermal pollution because now the river is 4 degrees warmer than it should have been because it's absorbed all this energy from the nuclear power plant. The benefits of nuclear power plants is this is a zero emissions plant which is producing a lot of electricity. The downside is once the nuclear fuel is spent, it's still radioactive and it's got to be guarded for like 10,000 years while it's dangerous. And so there's actually a lot of legacy costs after you're done producing electricity from that fuel. It's a problem for a long time. And these days, you also worry about terrorism too, because someone could steal the radioactive material, pack a normal bomb with it, and that is how someone would make a dirty bomb. And so radioactive spent fuel has to be guarded carefully. It can't just be put aside in a warehouse. It has to be guarded, and because of that, it is expensive and cumbersome, which is why wind and solar power are much better alternatives than nuclear power in fuel production or energy production. Breeder reactors generate nuclear power as well as additional fissionable material while fission is occurring. So in a breeder reactor, excess neutrons convert non-fissionable isotopes like uranium-238 to fissionable isotopes. And so you get more isotopes that can undergo fission and produce more energy through nuclear fission. The atomic bomb is a fission bomb. And so this bomb is just an uncontrolled chain reaction of splitting uranium, which releases a massive amount of energy. And one of these was dropped in World War II. The second bomb that was dropped in World War II was a hydrogen bomb, which is fusing hydrogen to helium. But a uranium bomb was dropped, and the amount of energy and the damage from one of these was substantial. And it was enough to bring the war to an end. And so the uncontrolled fission of uranium just releases a huge, huge amount of energy. Hazards of atomic bombs. You have the initial shock wave. There's an explosive pressure. A tremendous amount of heat is generated, and there is intense radiation, and an area may not be inhabitable for decades or even longer afterwards. And so there are a lot of downsides to nuclear weapons, which is why they are only used in the absolute last resort, and they have not been used since World War II. Nuclear fusion. This is taking light elements and fusing them into a heavier nucleus. Generally, hydrogen into helium. And this is tritium, the heaviest isotope of hydrogen, hydrogen-3. In the nucleus of tritium, you have 1 proton and 2 neutrons. And that fuses with 1 normal hydrogen to produce a helium nucleus plus a lot of energy. And here we see there's actually a mass difference. The energies are so great in the nucleus that you see mass differences. We go back to Einstein's work, E equals mc squared. Energy is mass times the speed of light squared. And the brilliance of this work showed that energy and mass are fundamentally the same stuff, just different manifestations of it. And so this mass loss is released as energy, which is why nuclear fusion releases a massive amount of energy, much, much more than even what we just saw. Fusion of hydrogen produces a lot more energy than the fission of uranium. And the potential for fusion is great because it could basically produce an infinite amount of energy for the world, and there's no radioactive fuel left over. Helium just floats into the atmosphere and escapes, but it's not like the radioactive nuclides from fission. And so this would be a much better way to run a nuclear power plant. Unfortunately, that hasn't happened yet. There are work on prototypes, but fusion hasn't been done controllably yet. So in which type of reaction do the nuclei of 2 light elements unite to form a heavier one? And that is fusion. That is a typo in the PowerPoints. So when 2 light elements unite and form a heavier nucleus, you get fusion. In a fusion reaction, two nuclei of hydrogen combine to form a nucleus of helium-4. Hydrogen is fused into helium, and that's exactly how the sun works. Which statement does not describe nuclear fusion? And that does not use uranium. Uranium is nuclear fission. Fusion uses hydrogen to form helium. Mass defect, the difference in mass between the actual mass of a nucleus and the sum of the masses of the protons and neutrons in the nucleus. Again, the mass effect occurs because there's so much energy in the nucleus that when mass is converted into energy, it's actually enough energy where you do see a small mass difference. And so for every gram of mass converted into energy, that releases 9 times 10 to the 13 joules of energy. And that is a really, really big amount of energy. All elements with atomic numbers greater than 92 are man-made and do not occur naturally. Uranium is 92, and that is the heaviest isotope found on Earth. Everything from 93 to 118 is man-made synthetically in high-energy particle accelerators. And there is a facility in Russia that still does this type of research, but we haven't discovered a new element since 118, and that's been over 10 years ago. So we may have finally pushed the periodic table to its absolute limit. And here we see the production of plutonium. So plutonium, which is the most important transuranium element because it's also used in fission-related things, was found to form from neptunium. So after uranium, 92, they found neptunium, which is 93, and plutonium, which is 94. Ionizing radiation. The radiation with enough energy to dislocate electrons and form ions. And alpha and beta particles, as well as gamma and X-rays, are all ionizing radiation. Because X-rays are ionizing radiation, we only use it when it's medically necessary. Ionizing radiation will kill living cells because they form free radicals, which are dangerous and can destroy DNA. Sometimes we use radiation on purpose to kill things, like in cancer treatments. You're purposely trying to use radiation to kill tumor cells and target the radiation to hit the tumor cells. So which of the following is true about ionizing radiation? All of the above. They separate electrons from atoms to form ions, which is why it's ionizing radiation. It can damage DNA molecules in both acute and chronic small doses. So if a large single dose or many small doses can be harmful to a person. And that is the end of chapter 18. With X-rays, one last thing, your cell is about 70% water. And so typically the first thing ionizing radiation hits when it hits your body is water. And it rips the water apart into hydroxyl radicals. And this is the actual species that's dangerous. If this touches a DNA molecule, it will rip it into shreds. And so ionizing radiation is damaging because it strikes the water that makes up 70% of our cells, ripping the water apart into ionizing radiation particles like hydroxyl radicals. And those are extremely damaging to biological molecules, especially DNA. And that is the end of chapter 18.